Hi everyone, in this video we will talk about a simple pendulum and how that connects to a simple harmonic motion. So in this screen to the left side you see the picture of a pendulum, and essentially the simple pendulum is made out of one long string that connects to a pendulum bob. The bob is a ball of mass, let's say m, and the string is massless. And at the start I have moved the pendulum away from its equilibrium position, which would be this point over here. That will be the equilibrium position, but I've moved it away. So because I've moved it away, you can see that there would be a restoring force. Now if we move over to the right hand side panel, we can here analyze all the different forces that are acting on the pendulum bob. So there's first the gravity, mass times acceleration due to gravity, that's acting vertically downward. Then there's the tension in the string, and the force of gravity then can be resolved into two perpendicular components, one parallel to the string and one perpendicular to the string. And so you can see that this perpendicular force will generate a restoring force, trying to restore the bob to its equilibrium position, which is this point over here. So that's what's going to cause our SHM. Okay, so I want to play this video once for you. So if I play this video, the pendulum bob oscillates like that. So it starts oscillating about its equilibrium position, and these oscillations form an SHM. So in this video we're going to try to analyze that SHM in terms of what we have learned so far. So first thing we have to do is to come up with an equation of motion. So we already have a free body diagram in this picture, and we will use that free body diagram and we will try to derive the equation of motion for this SHM in two different ways. The first way, we will use Newton's second law of rotation. Okay, so there is some rotation going on over here. The pendulum bob it's seemingly rotating about the point where the string is attached to this hinge point over here. And so we can try to come up with an equation describing this motion in terms of Newton's second law of rotation. Well, Newton's second law of rotation tells us that net torque, tau net, has to be equal to moment of inertia I times alpha, angular acceleration. Okay, so angular acceleration, what is that? Well, angular acceleration in this case is how fast phi is changing and how fast that change of phi is changing. So essentially it's a double derivative of phi with respect to time. That's the angular acceleration, d2 phi dt2. Moment of inertia of the ball, and notice that the ball is revolving or rotating about the hinge point. So and we will consider the ball to be a point object, so that's, we will not take into account the radius of the ball. So this is just one single point located at the center over here. And so the moment of inertia about the point of rotation, that I is just equal to m times distance squared, but the distance from the point of rotation to the point object that is rotating is L. It's the length of the string. So this I is equal to m times L squared. So that's the moment of inertia. So now we have alpha and I, and we need to know the net torque. Well, let's go back to our free body diagram. There are different forces. There's the gravity force, there's the tension force, but if you notice, the tension force is passing directly through the point of rotation, so this tension is probably not causing a torque. Similarly, the component of gravity that is parallel to the string is also not causing any torque, this mg cosine theta. The only leftover force is mg sine theta, or mg cosine phi, sorry. Mg sine phi is the force that is causing a torque, and that torque is equal to force multiplied by perpendicular distance. If you remember, tau equals F times r perpendicular. And the perpendicular distance again is L. So we can simply write this tau net is equal to mg sine phi multiplied by L. Okay, but now we have to make sure that we have the directions correct. If we think about it, mg sine phi is trying to bring the ball back to its a restoring force, so it's trying to bring the ball back to its equilibrium position. So this rotation is a clockwise rotation, so this torque is a clockwise torque. And now if I look at I times alpha, alpha is how fast phi is changing and how fast the change of phi is changing, essentially. That's phi is counted in the counterclockwise direction, so this I times alpha, that's counterclockwise. So in order for us to write tau net equals I alpha, we have to put both tau net and I alpha in the same direction, either both clockwise or both counterclockwise. So we can do that by writing mg sine phi times L is equal to negative I, which is ml squared, times alpha, which is d2 phi dt2. Okay, we can now just rearrange this equation. First of all, notice that the mass falls off from both sides of the equation. One of these L's cancel the L squared, so we are left over with an equation that looks like d2 phi dt2 plus g over L phi sine phi is equal to 0. So this is our differential equation using the first method. Okay, we're now going to use a second method to come to the same differential equation. It's kind of important to see the two different methods that one can use to get to the same. So we will use Newton's second law. This time we will only talk about translation. So let's think about what kind of translation is happening over here. Well, S, the arc length of the portion that the ball actually moved, that S is our translation. And so Newton's second law tells us F equals ma. Well, what is the force that is causing this motion? The force is mg sine phi. The perpendicular force is what is responsible for motion along that arc. So mg sine phi is the force, and that should be equal to negative m times double derivative of s with respect to time, and the negative sign comes because of the fact that mg sine phi and s are in opposite directions. Okay, so once again the m's cancel over here, so what we end up getting is d2s dt2 plus g sine phi is equal to 0. Note that this equation is slightly different. How can we write this second equation to look more like the first one? Well, we should we have an s over here, but there's a phi on the other side, so we really should try to express s in terms of phi. So how can we do that? Well, remember, s is the arc length of the circle and phi is the angle corresponding to that arc length, and where L is the radius of the circle, so we kind of know that s is equal to L times phi. So let me plug that into this equation. L is not changing, so the time derivative of L is 0, which means that we can just pull the L out of the derivative. So if we write d2 dt2 of L times phi, which is essentially the d2s dt2 part, this is equal to negative g sine phi is what we are going for from this equation over here. And I can pull the L out, so I get L d2 phi dt2 plus g sine phi equals 0. And now if I rearrange it, if I divide both sides of this equation by L, so divide this by L, divide that by L, 0 over L is just 0, so you see that I'll get back to that equation. So essentially our equation of motion looks like d2 phi dt2 plus g over L sine phi equals 0. I want you to compare this equation with our equation for SHM. So this is the equation for SHM that we came up with earlier when we were talking about the spring plus mass system. If we go back to our equation of motion, it looks like d2x dt2 plus k over mx, but remember k over m was nothing but omega squared. So really our equation looks like d2x dt2 plus omega squared x equals 0. That's the SHM equation of motion. If I compare that with the equation that we have so far, it is d2 phi dt2 plus g over L sine phi equals 0. Well, the d2 phi dt2 kind of looks like d2x dt2. The g over L, maybe it looks like omega squared. Omega, remember, is a constant. G over L is also a constant, so we can compare them. But sine of phi definitely does not look like x. So this equation is slightly away from the SHM. Not exactly SHM. Okay, so what do we do about it? So what we can do about it is we can make an approximation. So we need more input, and we are going to make an approximation. We're going to approximate phi. So we will say that phi is less than 4 degrees. So if phi is less than 4 degrees, and you can check this, you will see that sine of phi is roughly equal to phi. And you can check this with a calculator. You can just plug in the value phi equals 4 degrees or less. You can plug in, let's say, phi equals 3 degrees or 2 degrees, and then calculate both sine of phi, and you can check that sine of phi is roughly equal to phi. So with that check, with this approximation, if I now plug this into my original equation, which is this one, then the new equation that I will get would look like d2 phi dt2 plus g over L. And remember, I'm approximating sine phi by phi, and this is only possible for phi smaller than 4 degrees. So this is often called a small angle approximation. Small angle approximation. So if I can make that small angle approximation, then the new equation that I get looks like d2 phi dt2 plus g over L phi is equal to 0. And g over L being a constant looks like omega squared. Note that we have come back to our equation for an SHM. So for small angle oscillations, a pendulum really looks like an SHM. Okay, so now that we have found the equation of motion for the SHM, which is this one, we can go ahead and solve that equation of motion. The solution is just exactly same as what we did for the spring and a mass, except now that m and the k are replaced by g and l, different constants, different numbers, different values. Physically, they still represent the same angular frequency. So our new equation is d2 phi dt2 plus g over L phi equals 0, where phi is a sine omega t plus delta, with omega square equals g over L. So what does this tell us? It tells us the amplitude of oscillations is going to be this number a, the variable in front, the coefficient in front of the sine term. The angular frequency omega is now square root of g over L, right? So omega squared is g over L, so omega is square root of g over L. The period t equals 2 pi over omega, so t equals 2 pi over omega, and if I plug in omega equals square root g over L, then I get t equals 2 pi root L over g. And the frequency is f equals root L over g. One last thing to note is that this amplitude of oscillations, if you go back to your spring and mass system, if you remember, the amplitude itself was this x max over there, right? So that was the maximum expansion in the spring. So what was the dimensions of this quantity? Well, this quantity had dimensions of length, right? Because it's a length. Well, going back to our oscillations for the pendulum, the amplitude of oscillations in this equation, this A, is really an angle. If I do a dimensional analysis over here, this side, the phi, that is an angle, and sine of an angle, that's just a number. So this amplitude here better also be an angle. So that's the idea. The amplitude of oscillations in the case of our pendulum is just an angle. Okay, so this is pretty much covers simple harmonic motion for a pendulum. I hope you enjoyed this video.